Okay, welcome to Unit 4. Believe it or not, we are halfway through the Data Structures and Algorithms course. Today we're going to begin a study of hash tables. We will not be making any new abstract data sets in this unit. We will be making sets and maps again, just like we did in Unit 3. But we will be doing it with a different backing data structure. So instead of a binary tree, we'll be using what's called a hash table. Now, I want you to consider the following situation. Suppose we wish to make a searchable collection of all the words in the English language to be used in some application, such as a spell checker or predictive text application. And I find it easier for me to wrap my mind around a spell checker, but this is the one that needs the real speed. So anyone that's ever started typing into a Google search bar, things like you see those predictive text algorithms are where it's at, especially since we don't have full keyboards always on our cell phone. They need to be fast, really fast. Okay, so I want you to think about that. We want to have a collection of all the words in the English language that we can, use to check spelling or something like that, and we want it fast. Considering that there are approximately 150,000 words in the English dictionary, let's consider our options for what we have studied so far. So, understand the situation. We want to be able to look up and find words in an English dictionary. And of course, that's only 150,000 words. In reality, we could be dealing with customers on Amazon, or this could be, big data is where it's at right now. This could be millions or even billions of data items. Okay? We want to be able to access a specific item. So the first thing you might think of is let's put all the words, all our data items, but let's stick with the English dictionary. Let's put all the words in alphabetical order. Right? So we start with A, and then, A, apple, aardvark, whatever, right? All the way to zebra. What's the advantage of having a sorted array? Well, the chief advantage of a sorted array is that we can use what's called a binary search. Please do not confuse binary search with binary search tree. They sound similar, they're not. A binary search is for searching an array that is in sorted order, and we usually learn about it in an AP computer science class. It's the binary search is where you look at something and say, okay, let's say I'm trying to find a word in the dictionary, and that word is frog, and I just open the dictionary. Back in the day, y'all, dictionaries were not websites, they were actual books. You would open it up right in the middle of the book, and you would see, okay, I'm in the M's. And you would say, I've gone too far. So I cut the dictionary in half, and I'd say, okay, I'll open that half. And then you keep doing that back and forth, and it cuts down. Now, the binary search has a retrieval time of O log n, because we're repeatedly dividing all the possibilities in half. Half, 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 half. If you're playing a number guessing game, I say pick a number 1 through 100, and you pick one. And if I say a number, if I say 50 and you say higher or lower, and then say, okay, 75, and you say lower. Anyway, we're only going to play that game log of 100 times. Log base 2, technically 100 times. So we're only going to be able to play about 7 rounds. Eventually, I'm going to get it. All right. Well, that's pretty darn fast retrieval time, okay? I would argue, though, that the insertion time in this sorted array, think about how I would insert it. First of all, I wouldn't want to use an array at all, right? I probably want to use an array list because an array is not expandable. But if I'm keeping the English language, in a sorted, and all of a sudden someone, hey, we need to add a word to the dictionary. What is it called? It's called social distancing. I have to go and find that word. We add new words all the time. That addition time means I got to scoot everything back. So I'd have to find where it is in the list, insert it, and then everything else move back. That's O(n). So yeah, this is a good fast retrieval time. I like that. This is bleh, right? That's kind of sad. Hopefully we don't have to do that too often. So definitely a sorted array. It's an option because it does have a fast retrieval time with the binary search, but insertion time, if you're going to be inserting a lot, that's not a very good data structure. All right, let's take a look at our next option. Let me scoot this down just a little bit. What about a linked list, right? We learned about that. So this would be, our option 2 comes from our unit 2. Linked lists were great for making stacks and queues. Remember that? We could add to the front 01. We could add to the back 01 if it was a doubly linked list. Super fast, right? But what when you have to retrieve something from a linked list, right? So if I've got a linked list here, okay, of all the words in the English language, remember each little node links to the next node in the way. Well, the only way, even if I have it sorted, okay, the only way for me to get to this node right here is to start here and say .next, 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 .next. So on average, in order for me to get to an item in my linked list, I got to go through every one of them. So this is called the stupidest idea you could have for this problem. A linked list is a terrible idea because in retrieval time, predictive text application, checking every letter, rechecking, that would seriously cause for a slow experience, even with a fast computer. All right. Next, let's talk about another one. Binary search tree. Now we're talking. That was a fun data structure. We spent a long time studying that in Unit 3. Let's talk about the retrieval time for a binary search tree. There's binary search trees behave like a binary search. I mean, you have this, you start at the root, right? So when we're trying to look up a word, we would start here and say, okay, our word we're looking for is bigger. We go that way. We just cut off half the stuff. Then we would go to here, that just cut off half the stuff. So it turns out we're doing that constant dividing it in 2. That gives me a retrieval time of log n. That's right. That's right. Okay, so that's not bad. The insertion time here is a lot better than the sorted array. Log n as well. So definitely out of these 3 choices, a binary search tree. I'd like to present you with a new option today. Dun 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 dun, the hash table. A data structure where each item is stored in a specific index of an array based on a mathematical function is called a hash table. The mathematical function that determines its index is called the hash function. The process of assigning a hash code value to a data item is called hashing. A hashing plan for the English words. Let's take a look at it. So a hashing plan for English, we're going to put in English words here in our hashing function. Okay, let's just imagine what that would be. So what we're looking for is to take in a word like pumpkin, okay? And I'm going to put it in my little machine here, and it's going to spit out a number. And then I'm going to go, that number represents an index in an array. So I'm going to go there, and that's where it's going to be, right there. Okay? And that's it. Simple, right? So if I want to find pumpkin again later, I just, if someone says, hey, find pumpkin, I just put in my hash function, get the array, and boom, there's my data item, right? You can see how that can make for a very effective set or map. The question is, how do we do this, right? So our hash function has to follow what's called a hash contract. So the hash contract says that 2 identical data elements, whatever it is that you're calling them identical. I'm not saying the same object. I'm saying they have the same data value. So, for example, the word pumpkin, all in lowercase, is the same as the word pumpkin, all in lowercase, right? 2 words are the same. They're identical. They must produce the same hash value. So we have a bad hash function. We are not fulfilling our hash contract if our hash function sometimes produces one number, sometimes another. Well, that's what that star is for. Let me come back to that star. There's a little subtlety I want to talk about there later, but that's the idea. They need to make the same value every time. Okay, so it can't be like random. All right, and here's the deal. The other part of the contract is that the number of non-identical elements with the same hash value is kept to a reasonably small number. This is so key to understand. You see, I'm not saying that two words that are different will not have the same hash code. It is totally possible that pumpkin that was 22508559 and maybe jalapeno is also 22508559. I am guaranteeing that pumpkin will always give the same number, but I'm not guaranteeing that that's the only word that would give that number. So, because I don't say that. I say that the times that two different things give the same number is relatively small. So I'm saying it's rare, but it can happen. Okay? All right. Let me talk about this little caveat right quick, though. It is possible, and we will see that over time, hash values that are produced can change, but they need to change in a consistent way. So, for example, I'm putting in pumpkin into a hash table. It presents 22508559. Later on, I may have to change that hash value, but if I do decide to change it, I need to change it and then make sure that the change is still applicable later. That when I look it up, that new number is still there. So it just needs to be consistent. You can certainly change it in the same way you can change your password, but it just needs to be consistent. Okay. Some definition here again. When a hash function produces the same number code for two different objects, we call that a collision. So most of the stuff we're going to be talking about is how to handle collisions. Okay? Because making a hash table is super easy. It's what do you do when there's collisions? All right? So suppose we want to make a hash table for all the words of length 12 or less. Let's think about that. Just for simplicity, all the words that are length 12 or less. A, apple, aardvark, but no mononucleose, because mononucleose is ultramicroscopic mononucleose or whatever that stuff is, right? Just 12 letter words. Okay, so let's think of things that we could do. I have one possible idea, and I want us to look at the pros and cons of them. The first hashing function we could do is, why don't we add the letter values? Right? Let's think about what that would look like. So you're adding the letter values. So if I had something like, I don't know, dog, or and let's just stick with lowercase, like dog. Okay, well, D is we could do their ASCII value, but D is A, B, C, D. It's the fourth, so that would be the fourth letter, and then the O. Oh gosh, I don't even know. I don't know, what is that, like the 20th or 18th letter, something like that. Something like that. Okay, don't kill me if I get that wrong. And then G is D, A, B, C, D, E, F, G. That's like the seventh. Okay, so we could add them all up, and we would get a hash code function, right? 22, and then that's like a 29. Okay, assuming that my O is correct. All right, well, this is a pretty bad idea because it's going to violate our hash function contract. All right, I'm hearing that it's 15. Thank you. All right, so I got to take off 3, so 26. All right, that feels good. It was bothering me that I didn't really know it. But this is going to violate our hash table function because you know what? I can immediately think of a word that has the same one, right? We don't want, then it's okay to have some collisions, but not too many. Well, this is going to give us way too many. All right, I've got, how about bear, right? That, believe it or not, I believe, if my notes are correct, bear also equals 26. So I'm just thinking about animals right here. So yeah, anytime the letters are the same but in a different order, it's going to collide, and then also completely different sets of letters. This is just way too many collisions. It's not giving a good enough number. All right, so I got a better idea, right? Or what I think might be a better idea. All right, so what about adding the letters with their place value, right? This is going to be a very different story. So, oh look, I got the notes right here about the values. All right, so let's take a look at our collision we had earlier. We have dog, right? So dog, when I take their place value, this is going to be a different number. See, I've got D is 4, and I'm going to multiply it times 26 because I have 26 letters, and this is 0, 1, 2. If this reminds you of converting from different number bases, then good, because it does. And this is kind of related. Then the O is 15, and then we got times 26 to the first, and then I'll call the G 7, and then that'll be times 26 to the 0, which is just a 1. That's going to work out to be 5, 1, 2, 6. And now if I try and do GOD, then I would get 7 times 26 to the second, plus 15 times 26 to the first, plus 4, and that is 3101. For all 12-letter words, this is going to give us, and my guess is no collisions. I can't really think of a way that it possibly could. And the reason why is because we're doing those powers of 26. That each, because we can only add between 1 and 26 for each letter. There's no way that a 2-letter word is going to have the same sum as a 3-letter word. And clearly 2 words that have different ordered letters are going to have a different sum. So that should give us a unique value. So this is a pretty good scheme. Or is it? It turns out this is also a bad idea. It doesn't violate our hash table contract. It just becomes completely unnecessary, and it's not taking advantage of our hash table contract loopholes. What kind of array would I need here? I would need an array that can store all possible words that are 12 letters long. So that's 26 to the 12th, plus 26 to the 11th, plus 26 to the 10th, plus 26 to the 9th, all the way down to 26. That would result in, I think I did the math earlier, and hopefully I'm right, this sized array. That's how big an array we would need to have absolutely no collisions. Now, this is stupid for many reasons. I mean, one, the English language only has about 150,000 12-letter words to begin with. Why are we making an array that big? Well, because we have to make the array big enough to handle all possible values of our hash function. So we've written a hash function that gives me a range of values so much bigger than the possible number of things I need to store. Now, this exceeds the maximum array size in Java anyway. This is a memory error. This cannot happen. We can't do this even if we wanted to do it. Okay? So it doesn't work. Let's come up with a better idea. The better idea is for us to allow for some collision, just not too much. So our best idea would be to do something with modulo, everyone's favorite computer science operator. So what we want to do is to use the sum of the powers of 26, but modulo a reasonable hash table size. And that's what we're always going to do. There's always going to be whatever hash table size I want, that we're going to take all these possibilities here, okay? And we're just going to mod them down to my hash table size. So if I want a hash table of size 100,000, then I'll just mod it by 100,000. And when you mod by 100,000, that gives you possible results between 0 and 100,000. How often will they be exactly the same? Well, every so often, two numbers have the same modulo 100,000, but not very often, right? In the English language, but there's only 150,000 words, so how many of them have the same modulo? Not very many, maybe just a few. All right, so one of the tricks, though, is at any one of these points, we would be exceeding the length of an int. So it's usually a good idea. You could use longs, but you could easily exceed long as well, is that you want to modulo as you go. And the modulo arithmetic allows us to take modulo of products before we even multiply. You don't have to multiply, then take the mod. You can take the mod before you multiply. Then you can add, take the mod again, and then finally take the mod one more time at the end. So that's the best idea. What size table should we use to modulo? That just depends on the number of elements we plan to add. So a small table, if we were to make this a hash table of size 100, we're going to have a lot more collisions. And you'll see the more collisions, the slower the hash table. The bigger the hash table, the less collisions. But so that's going to be fast retrieval, fast add. But you have a lot of wasted space, because if you have very little, if you're going to make sure you have very little collisions, you're going to have to definitely end up, just by your strategy, having hash function numbers that will never be used. Right? If I knew exactly what numbers would be used, then I would just make my array exactly that size. I need the story, but that's not the situation. We don't know exactly all the numbers that would happen. So in order to make sure you never have, or try to never have one, you're going to end up having a lot of wasted space, and it's not that bad to have a couple collisions. So that brings us to the hash size balancing act. So how big a hash table do I want? How big is my array going to be? So if I use a smaller hash table size, I do have some pros. First of all, lower memory usage. I know, not that big a deal with today's modern computers, but it's still something to consider. But we get a fast iteration time. The only way to iterate through a hash table, unfortunately, is to just start at index 0 and just iterate through. And if there's something there, visit it. If there's not, skip it. If you have a hash table that's huge, you're going to have lots of spaces in that array that are completely vacant. And so you're going to be wasting time visiting empty spaces and then deciding to skip over them, because you only skip over them when you realize they're null. So, because they'll be null in spaces you haven't used. The cons of small hash type: real slow add time, because you're slowing. Once you have too many collisions, you have to handle collisions, and we haven't gotten there yet. But you can imagine handling collisions means you have to do something else. Slower retrieval time, because if you have collisions, then when you go to retrieve it, then you gotta like undo all that collision handling algorithm to kind of trace back your steps. And then of course that makes for a slower removal as well. If you have a larger hash time, you're going to get a fast add time, fast retrieval, and a fast remove, but your iteration will be slower, and you have excessive memory usage, and then you're just kind of cheesy to maybe too big a large hash size. Easy answer is this: the hash table size rule of thumb. The hash table rule of thumb is that you want to have a hash table roughly twice the size of the number of items you want to store. So that means that if I have 150,000 12-letter words in the English language, I should roughly use a hash table of about 300,000. Okay? But there's one more little caveat. Okay? You want to pick a number that has very few. You don't want a hash table size of a number that's going to have lots of collisions because we're doing modulo, right? And I want my modulo numbers to be really unique. And it turns out that using a prime number would be better. Okay? So you want to there's plenty of ways to look it up. You could write a little algorithm for it. There is next probable prime. But you want to in general use a prime number. That helps to decrease collisions or how you handle them, especially with the different chaining. So that's usually what people say: use the first prime number roughly twice the size of the number of items you want to put in. If you know the number of items. If you don't, then you really can't say, right? And so what we'll do when we don't know the items is that we'll just expand it. We'll start with a reasonably sized hash table. Once it starts getting too many items, and we'll talk about what to do. We'll say, all right, let's make a new hash table. But when you make that new hash table, that's when you have to redo your hash code because you have different modulo. But as long as you're still using that same code, it'll work fine. All right, so now we're ready to talk about collisions. Okay, so there's two basic ways to do it. To handle collisions, you can use a list to store those multiple collisions, like in an array list. So, that basically what happens is that if you have the word dog, if it happened to go to the same place as the word cantaloupe, that you would just, at that index in the array, you don't have a word, you have a list of words. And so now your list is, dog and cantaloupe. And then when you go to retrieve, you go to that thing and you say, okay, let me just keep going down this list and find it. The other way to do it is called probing. There's something called linear probing. And then you'll even hear about quadratic probing. What that says is that, okay, so say I get an index of like 2047 from my hash code function. I go there. Oh, man, array index 2047 is already full up. So then I put it in my linear probing formula, which gives me the next possible one I should use. It's just a formula that takes an index and spits out what's the next one. I see if it's available. If it's not available, it sends me the next one and the next one. And as long as I'm using a defined algebraic rule, when I go to retrieve it, I will be able to find it because I'll just follow the same steps. And you can even use something called quadratic probing, using a quadratic instead of a linear function, which supposedly is even faster. The merits of each are debatable. Most people, as I research, seems to say that probing is better. They say it's faster and has other things. It's more difficult to me to code, and many college courses will definitely cover it. It's interesting. I'm not going to. We're going to just look at separate chaining in this class because I think it's easier to understand, and we're going for our fundamentals here. So, with that being said, let's take a look at our first kind of idea. How to make a hash table using a separate chaining to handle the collisions. First, you make your hash table, which is going to be it's going to be an array. And I'm not sure why I'm missing. So this needs to have brackets right here. Yeah, it's going to be an array. So you make an array. You declare that it's going to be an array of type list. Okay? So then when you instantiate it, like in your constructor, you'll say new. I'm using our list array that we made a long time ago. You could probably use java.util.ArrayList bracket get hash size. That get hash size would be a method that computes what size hash table you want. So that's how it's done. You make an array of array lists, almost like a matrix. Okay? So how do we add to a hash table using separate chaining? First, you compute the hash code with your hash code function. Then you go to that and you see if that array list is still null at that index. If it is, create a new array list and pop it there. If it's not null, just add it to the back. One way to do this, if you want to keep the code really simple, is when you create your hash table, you can actually go through and initialize all your lists to being empty. That will make the creation time ON, but you're only doing it once, so it's still functionally fast. So a lot of people like to do that. That just cuts down the amount of writing. Next thing you could do, we need to talk about how to remove. So how do I remove? First, you compute the hash code for the element. Then you go to that index, and you just go down one at a time through all the elements at that index until you find what you're looking for and remove it. Same thing with accessing. You find the item. You find the item's hash code index. You go there, and you just go one at a time down the list till you find it. And you return that element. So here's just kind of a picture of what might happen. Let's say we're doing our hash table of words. So here's my hash code. You can see I have some of my lists are still null because they've never been initialized. Smile is the only one there, and they have happy, camper, park, school, carrot, and appetizer are all at this index. Now this, in actuality, would be kind of rare. Right? It's pretty unlikely that we'd have 3 collisions at this one index. But keep in mind, how long does it take a computer to search? Yes, technically, this would be ON to go through this, but it's not it's not really ON. N is in the entire state, items in the data set. To loop through an array list of size 3 is 3 steps. That's virtually automatic. That is extremely fast. So that's not going to in any way slow down our retrieval that we have to go through 3 items. Now, if this list here at index 243772, if it were, a million items, that would be slow, right? But even 100, but you're not going to have more than 2 or 3. So that's pretty much it for this lesson. And now we're just going to get right into doing it.